Hi, and thank you all for subscribing to this fifth session of a series of webinars dedicated to data science. Today we'll be talking about analysis of variance, also known as ANOVA. My name is Jean-Paul Maalouf. I'm a statistical consultant at Addinsoft, which develops the XLSTAT software. I will be using XLSTAT to run some demonstrations on the analysis of variance. So analysis of variance, or ANOVA, includes a broad world of techniques. Unfortunately, today we only be able to see an overview of these techniques and how to implement some basic ANOVA models in XLSTAT. So I would strongly advise you to run some more research if you'd like to go further on ANOVA or request some trainings from XLSTAT. At the end of the webinar, there will be a Q&A session during which I'll be able to answer the questions you ask. So you may submit your questions in the chatting window, and I'll try to answer as many questions as I can at the end of the webinar. The handouts of the presentation may be downloaded, as well as the data I'll be using for the demonstrations. So there should be a button somewhere on the webinar platform in which you can download the data. So I would advise you to download the handouts because you will find many useful links inside the PDF. So what will we be talking about today? I'll start with a few words on XLSTAT. Then I will show you my usual way of dividing the statistical tools into several families of tools. Then I will tell you a small reminder about statistical testing and statistical modeling. Those were the topics of the two previous webinars we had together, and they are essential in order to understand some sides of the analysis of variance. So I will start talking about analysis of variance in the first part of the webinar. Then I will be talking about assumptions about residuals. So residuals are quantities that are computed every time you run a statistical model, and I will remind you what they correspond to. Then I will be talking about multiple pairwise comparisons. What are multiple pairwise comparisons in ANOVA? Then we'll switch to the Kruskal-Wallis test, which is a non-parametric equivalent to the one-way ANOVA. I will do a small reminder on what a non-parametric test is. And at last, I will end the webinar with the two-way ANOVA and the interaction effects. Who are we? XLSTAT is a statistical software that works as an add-on to Excel in PC and in Mac. So it's developed by the Addinsoft company, and it's also available in Excel 365 and Google Sheets, so you're able to use it on the cloud. One of the main strengths of XLSTAT is that it works in the Excel interface, so it allows you to run statistical methods from the most basic method to the most complex one, all inside Excel. So from the configuration of the analysis to the customization of the results, everything happens within the user-friendly Excel interface. In a few numbers, XLSTAT has more than 200 statistical features, 220. It has more than 150K users worldwide, more than 25 employees at your service, more than 300K monthly visits on the website. It's available in 7 languages, and we have offices in 3 time zones across the globe, so America, Europe, and Japan. There are 10K monthly downloads of the software. XLSTAT is developed by the Addinsoft company, which is located in the data factory in Bordeaux, France. So this is a private lab dedicated to data science that includes 5 expert companies around data science, including the Addinsoft company. It's very active in terms of data science as it organizes more than 25 workshops, events, and trainings every year. XLSTAT is available in 8 different solutions to meet your very specific needs. There are 3 generalist solutions: Basic, Basic Plus, and Premium. Basic allows exploring, visualizing, modeling, and testing your data in one single interface. So there are around 100 statistical features which are essential included in this solution. Basic Plus has all basic features plus essential machine learning tools. The premium solution has the complete 220 XLSTAT features. Then between Basic Plus and Premium, you have many field-oriented solutions, which are less generalist. So Sensory is for sensometricians, so it includes features for product optimization in terms of sensory attributes such as preference mapping or product characterization or discrimination tests. Then Life Sciences is dedicated to biostatisticians or people who work in the medical field for the analysis of medical and biological data. Marketing has some specific tools for market research and strategy, including conjoint analysis. Forecasting has specific tools for the analysis of time series and risk analysis. Quality proposes tools such as design of experiments and SPC for quality control. The XLSTAT website holds more than 200 tutorials associated to downloadable datasets. So each XLSTAT feature is linked to a specific tutorial online, which guides you through the analysis process from the configuration of the dialog box to the interpretation of the result with a real-world data in Excel. XLSTAT also develops the StatCafe YouTube channel, which presents short format videos, and which each video presents one specific feature and an application using XLSTAT. So here are the families of statistical tools I've been talking about during the last webinars. So we've talked already about descriptive statistics, which allow describing one variable or the link between two variables. So we spoke about univariate or bivariate statistics when we had the webinar on descriptive statistics. So we talked about the mean, the standard deviation, histograms, box plots. We also talked about scatter plots and other interesting tools. Then in the exploratory tools and clustering tools, we used methods such as PCA or principal component analysis to easily extract information from a large data set without necessarily having a precise question to answer. We also used AHC to cluster our data into groups of similar observations. Then statistical testing includes methods that help you accept or reject a very precise hypothesis, assuming error risks. So we played around with the t-test, the chi-square, and correlation tests. Statistical modeling allows understanding how a variable behaves according to a set of other variables and optionally make predictions. So the last webinar we had together, that was last week, we spoke about what statistical modeling is, and we also developed the example of the linear regression. Today we'll be talking a little bit more about ANOVA. So notice that ANOVA can be considered at the same time as a statistical modeling method and as a statistical test. And the main difference between regression and ANOVA is that regression allows explaining one quantitative variable according to quantitative variables, whereas ANOVA allows explaining quantitative variables according to qualitative variables. So today we'll be focusing on this one. You have a link to all previous webinar recordings by clicking here. Next week there will be a new webinar we've just programmed, a webinar on supervised machine learning and prediction, during which I will be talking about how to optimize an algorithm in terms of predictive quality. So this will be an introduction to supervised machine learning. So you have the subscription link here. Here's a small reminder about statistical testing and statistical modeling, which are two sides of the ANOVA method. I will start with statistical testing. So I remind you that statistical tests allow answering questions such as this one. This is a very simple question we may ask in the framework of statistical testing. Is mean A significantly different from mean B, or average A significantly different from average B? Statistical tests involve two hypotheses. One hypothesis that we call the null hypothesis, which generally implies an idea of equality. So mean A equals mean B. On the other hand, we have an alternative hypothesis, which generally implies an idea of a difference. So according to this hypothesis, mean A is different from mean B. Now, how to interpret the output of a statistical test? A statistical test provides a number that we call the p-value, which is a probability number, so it's bounded between 0 and 1. And this p-value represents the risk you take of being wrong while rejecting the null hypothesis and accepting the alternative hypothesis. This is not the very precise statistical definition of the p-value. It's a small shortcut that allows you better understand it. Okay. Usually we compare the p-value to a risk threshold, which we call alpha, and we reject the null hypothesis if the p-value is lower than alpha. And alpha should be chosen by the user, by yourself, according to how conservative you want to be in taking a decision or not. The more you lower alpha, the more conservative you will be by taking your decision. You have a recording on statistical testing through this link. So globally, if your p-value is very low, usually you say that you have a significant effect. And in this example, this would mean that the mean A is significantly different from mean B. So you are accepting the alternative hypothesis. Then let me talk about statistical modeling now. So I remind you that statistical modeling allowed us to model a specific variable according to a set of other variables. And we used this data set to illustrate this. So this is the data of clients from an online shoe selling platform. The clients are stored in rows, as you can see, and they are characterized by several variables in columns. These variables are either quantitative, such as invoice amount, time spent on site, weight, shoe size, height, and we also have qualitative variables such as origin, gender, or preferred brand. So variables which are expressed in terms of categories and that cannot be expressed in terms of numbers. Okay. So we had asked a question last time. How does invoice amount, in green, vary according to time spent on site? So we want to explain one variable, which we call the dependent variable, the invoice amount, according to time spent on site. So we used a specific model, which we call the linear regression or simple linear regression, to investigate this question. Now, this is not the only model that exists to link one specific quantitative variable to another, but I just chose it for convenience. It's the easiest model to explain. So I chose linear regression to model invoice amount according to time spent on site, and this is the shape of a simple linear regression. It's a straight line. Invoice amount is the dependent variable which we place on the y-axis, and time spent on site is the independent variable which I placed on the x-axis. This is the equation of my linear regression. So as you can see, a statistical model links the dependent variable to the independent variable through an equation using parameters in orange, or coefficients. So this is my way of simplifying reality, a straight line model. A will represent the intercept. This will be the y coordinate of the intersection point between the y-axis and the model, or the straight line. And B will be the slope of the line. So if b is negative, then the slope is decreasing, or the line is decreasing. If b is positive, then the line is increasing, the relationship is positive. And if b equals 0, then the line is flat. Here you see that there's a part of reality that wasn't captured by the model. The model doesn't really passes through all the points. And this part of reality that we represent by all the differences between the points and the model, we call it the residuals or the errors. This is the part of reality our model was unable to capture. We've seen last time that in order to have a reliable model, there are some assumptions about residuals that should be respected or verified. It will be the same with ANOVA. The only difference is that instead of having a quantitative variable on the x-axis, so instead of having quantitative explanatory variables, we will have qualitative explanatory variables, and we will still have residuals. So what is analysis of variance or ANOVA? Imagine now we want to explain this same dependent variable, so invoice amount, according this time to origin, which is qualitative. Here's the question. How does invoice amount vary according to origin? Now, ANOVA is a model, but said in other terms, ANOVA can also be considered as a tool to compare means simply. So we'll simply be comparing the means of each origins and try to see if there's a mean of invoice amount for a specific origin that is different from the mean of invoice amount from another origin. Okay? Here's how we can represent things graphically. Look, this is the dependent variable, invoice amount, which is quantitative. And this is the qualitative explanatory or independent variable, which we call factor in ANOVA, the origin. And what I represented in orange is the averages or the mean for each origin. And of course, these are the factor levels or the qualitative explanatory variable levels, Earth, Mars, and Pluto. So basically, we'll simply be comparing the three means. So what is ANOVA? ANOVA, or analysis of variance, is a model used to explain one quantitative variable by one or several qualitative variables we call factors. And in simpler words, ANOVA helps comparing means of different groups of observations, for example, the mean invoice amount from different origins. And when you only have one factor involved, we talk about one-way ANOVA. So in this case, we only have one factor, which is origin. So we talk about one-way ANOVA. Further in the webinar, we'll see a case where we'll investigate two explanatory variables, two factors, and therefore we'll be talking about two-way ANOVA. Now let me show you why we call ANOVA a statistical model. So in this chart, you have invoice amount on Y and the different categories, of course, of origins, and the green dashes are the data points, okay? And the crosses, the red crosses, are the means. So ANOVA as a model can be represented simply by the means of the different levels of the explanatory variable. And the statistical model involves residuals, as I told you. Now, where are the residuals hidden? Well, the residuals are simply all the differences between the data points and the model. So this would be all the differences between the green dashes and the means. Here are the residuals. So we'll have to verify the residuals assumptions on these quantities represented by red arrows. Here's the data set we'll be working on until the end of the webinar. A data set where the spiciness of three sauces has been evaluated by judges. Here you see that you have three sauces, S1, S2, and S3, and each one of them has been tasted several times, and the spiciness every time has been recorded. The question we ask, does spiciness change according to the sauce, S1, S2, and S3? So which one is the dependent variable? This is spiciness. This is the variable we want to explain. The independent variable or explanatory variable is simply the sauce, which is right here. So what would be the first thing to do maybe before running any test, which is my big recommendation since the beginning? Before running any statistical test, I strongly recommend you to describe your data, to visualize your data, to see if there's no weird pattern, if there's no extreme outlier, which is due maybe to an error in the recording of your data, or I don't know, which corresponds to an observation which is not part of your global population. It's very important always to visualize your data. So here's one kind of data visualization, multiple box plots according to the sauce, and the spiciness on the y-axis, of course. So here we don't really see weird patterns in these data. We don't really have like outliers. We don't have distributions which are very dissimilar or unsymmetrical. Maybe in this specific box plot, so linked to S2, we have a mean, the red cross, which is a little bit far away below the median, which is this black dash. So this means that maybe there's a small skew of the distribution towards lower values, but it's not very big, it's not very important. I think we can carry on with the ANOVA, but please do visualize your data before running any test. So in order to obtain this kind of charts, you can watch the descriptive statistics webinar in case you haven't watched it yet. So the ANOVA involves a statistical test, and a statistical test involves hypothesis. So these are the spiciness means according to sauce, and these are the hypothesis of my ANOVA. So the null hypothesis implies an idea of equality, as we've seen earlier, most of the time. So mean S1 equals mean S2 equals mean S3. The alternative hypothesis implies an idea of a difference. So at least one mean is different from another. The test will compute a p-value, and if the p-value is lower than alpha, we can reject the null hypothesis and accept the alternative hypothesis while taking a risk of being wrong proportional to the p-value. So let us set alpha to 0.05 for this webinar. Okay. Now, what's behind the ANOVA p-value? How is the statistical effect in ANOVA measured? And why do we say analysis of variance actually, while we are comparing means? So the ANOVA is based on the comparison of two variances. And I remind you that a variance measures the spread of the data. Actually, variance equals the square of the standard deviation. So there are two variances that are compared, two sources of variance that are compared behind ANOVA. The first source of variance is the variance of the residuals that is represented by the size of this red arrow. Okay, so this is the within group variance, or the residual error, the variance of the residuals. This variance is compared to the spread of the means, or the variance of the means, which is represented by this green arrow. So the bigger this green arrow compared to the red one, the more important the spread of the means is compared to the residuals, and the stronger your effect is. And actually, what ANOVA does behind is that it computes a ratio called the F ratio. which divides the between variance by the within variance, so the green one by the red one. So the higher the F ratio is, the stronger your group effect is. So the stronger your explanatory variable effect is. So when the F value increases, the P value decreases, the more you are likely to reject the null hypothesis. Now let us run our first ANOVA together. So here are my data points. Okay. And here's XLSTAT. Inside Excel, you have several menus containing different features that you can apply directly on your data in Excel. I will open the modeling data menu, which includes the ANOVA feature. There we go. This is a very typical XLSTAT dialog box, which includes several tabs in which you can capture data and configure options, customize options. And most of the XLSTAT modeling methods are organized the same way. So you have fields in which you can include dependent variables, so quantitative, in the case of ANOVA, and other fields in which you can include explanatory variables or independent variables. So in the case of ANOVA, these are qualitative. Now let me show you something funny. Look at the title of this dialog box. If I deactivate the qualitative explanatory variables, it will automatically activate the quantitative, and the title of the dialog box will switch to linear regression. So when you model quantitative data by quantitative, this is a case of linear regression. If you model quantitative data by qualitative data, this is ANOVA. If you model quantitative data by both qualitative and quantitative, you are running ANCOVA. And of course, I'm talking in the framework of the linear modeling. So there are many other types of models which are not necessarily linear, which exist out there. So now I will just stick to ANOVA. I will capture my spiciness data right here and my sauce data right here. So this is the explanatory variable or the independent variable. I can also select it like this until the end, but I won't be wasting time. I just select it like this, okay? Now I will click OK, and I obtain the results in a new Excel spreadsheet. I will go a little bit further down to comment on this table, which is quite important. So this table includes the two sources of variance, the between variance, so the spread of the means, and the within variance, this is the variance of the residuals. This is the F ratio, so it's the ratio between the green one and the red one. And the F ratio is linked to a p-value, which is right here. And this is the p-value of your one-way ANOVA, so which will help you answer your initial question and reject or not the null hypothesis. So the p-value is lower than the alpha threshold we chose earlier. We reject H0 and accept HA while taking a risk of 4.9% of being wrong. In the ANOVA dialog box, you have a charts tab that allows you to draw different types of charts. And here you get the chart I had showed you earlier. So spiciness according to sauce with the different means and confidence intervals. So let us answer the question now. At least one spiciness mean is different from another. This is the alternative hypothesis. So before going further, we still need to check the assumptions about residuals. This is a linear model. It's very important to do this. I remind you the assumptions about residuals we had already seen for regression. So residuals should be independent. There should be one measurement per individual. No link between two specific observations. We will see this a little bit later. Okay. The residuals should follow a normal distribution. There shouldn't be too many outliers. too many data points that are too far away from the bulk of the data. And the groups must have equal variances. So I will check each of these hypotheses apart, and I will show you tools to investigate at least the outliers, normality, and equal variances hypothesis. The independence hypothesis, I will just assume it. So we assume an independence, no obvious relationship between measurement. There's no good reason to think that observation 1 and observation 2 are correlated to one another. So the way I design my experiment doesn't really make me think that there's a link between these two observations. At least for now. You will see later on that there actually is a link. Then how can I check for outliers? Among the ANOVA outputs in XLSTAT, you will find this output that shows you the standardized residuals of all your observations. Okay, so each bar here corresponds to the residual linked to one specific observations, and you shouldn't have many observations linked to residuals that are too big according to the bulk of residuals. In this case, things are okay, I think. There's no residual really going too far away according to the bulk of the data. Then what about normality assumptions and variance equality assumptions? Within the ANOVA dialog box, you will see this tab that I will show you directly in XLSTAT. So let me get back just further up and click on this replay button to get the dialog box, which is automatically filled out. I will go to the Outputs tab and Test Assumptions subtab. I will activate Normality Test and Levene's test. These are tests that allow checking for normality of residuals and equality of variances. Levene's test is for the equality of variances, and I would recommend going for the Levene's test based on medians because it has a good compromise between power and robustness. So I click OK, and at the bottom of the report, I get the result about normality test and the result about variances. So here's the result about normality, and here are the hypotheses around the normality test. So according to the null hypothesis, the residuals follow a normal distribution. To the alternative hypothesis, the residuals do not follow a normal distribution. So the p-value is higher than alpha, so we can say that the distribution of residuals does not significantly differ from a normal distribution. Therefore, we are happy for this assumption. What about the assumption about variances now? We launched the Levene test, which implies a p-value and a null alternative hypothesis. So this is another way to write down the hypothesis of the Levene test. So according to H0, variances are equal, and to HA, at least one variance is different from another. As the p-value is higher than alpha, we do not reject the null hypothesis that states that variances are equal. So we are happy. Just one little thing about the test of normality. Please be very careful when using this test. It's really not reliable when you have a low number of observations. Only use it when you have enough observations in your data set. Okay. So our ANOVA results are reliable. So the answer to our question is clear now. We have adopted HA while taking a certain risk of being wrong. Now, can we know precisely which means differ from one another? We've only said that at least one mean, we don't know which, is different from another. Can we know which one? For this, we'll use multiple pairwise comparison procedures. So multiple comparison procedures help examining statistical significance of the differences between means of categories. These kind of procedures will help us, for instance, test all the pairwise differences. We'll test the difference between S1 and S2, between S1 and S3, and S2 and S3. So in this case, we'll run 3 additional tests. Now, the tricky thing about multiple comparisons is that they generally involve a penalization of p-values, and this penalization increases as the number of computed p-values increases. What do I mean by this? Every time you launch a statistical test, you are taking a certain risk of being wrong to make a decision. So imagine that here, instead of having only 3 sources, you had like 10. This really increases or multiplies the number of pairwise comparisons you have, and therefore the number of tests you will be running. So the bigger the number of tests you launch, the more likely you are to make at least one wrong decision, because every time you are taking a risk of making a wrong decision. So pairwise comparison procedures keep this risk low by penalizing the p-values as the number of tests involved increase. So the higher the number of tests involved, the stronger the penalization of the p-values will be. And a penalization of p-values simply means an increase of the value of the p-value. Okay. There are many common procedures of pairwise comparisons. For instance, Stucky HSD, which I recommend, or Fisher LSD, which is less conservative, so I don't really recommend it much. You have one which is commonly used, I think, in sensometrics. This is Newman-Kuhl's SNK. It's also used in agronomy, I think, but it has a very weak penalization, so it's not very recommended by statisticians. Otherwise, there's one which is very penalizing, Bonferroni. And there are some procedures that imply the comparisons of categories only to one specific category, for instance, a control category, biostatistics. So if you're not really interested by all the possible pairwise comparisons among categories, and you're only interested by comparing all the categories to one specific category, for instance, you want to compare all the new products to a legacy product in the market, you can use the donut comparisons, which allow you to save some comparisons and lower the penalization, make the penalization less stringent. So how to launch multiple comparisons in XLSTAT? Let me get back to the data. So I will click here, and under the Outputs tab, I will go to Means and activate multiple comparisons. And here, activate pairwise comparisons. And here you have all the procedures available in XLSTAT. You can choose among. I recommend taking Tucky, which is quite generalist. Otherwise, here you can activate comparisons to a control, as I told you. If you want to compare all the categories only to one specific category, you can use the donut. So I click OK. And I get the result, which appears at the bottom of the report. You will see that the multiple comparison procedure is expressed through several shapes. This one, and this chart, which I really like because it's quite synthetic. In this chart, you see the mean estimation by the model of the spiciness of each sauce. So in red, you have sauce number 3, in blue, sauce number 1, and in green, sauce number 2. You see that each category is linked to a few letters. These letters will help us interpret the multiple comparison outputs. Two means having at least one letter in common are not significantly different. This is the case of S3 versus S1, so the red versus the blue. Look, they have one letter in common, this is letter A, so they are not significantly different. Otherwise, two means without any letter in common are significantly different. This is the case of the red one and the green one. A and B, they don't have any letter in common. If you take the blue one and the green one, you see that they have the B in common, so they are not significantly different. So finally, the S3 sauce is the spiciest one, the S2 sauce is the least spicy, and S3 and S2 are significantly different. Now we had this statistical significance solution. It's always quite important to go back always to the interpretation of the real numbers in data. So look here, the score of spiciness for the red sauce is around 5.5, whereas the green one is around like 4.5. Okay, so there's more or less roughly a difference of one score of spiciness. So although this difference is statistically significant, does it really make sense in terms of your own field of expertise, in this case sensometrics? Always get back to the data and try to interpret things within your field of expertise. So let me talk to you about the Kruskal-Wallis test now that we're done with the one-way ANOVA. This is a non-parametric equivalent to the one-way ANOVA. What does this mean? In case the assumptions about residuals are violated, one solution among others is to replace the one-way ANOVA by the Kruskal-Wallis test, which is a non-parametric equivalent. So as a non-parametric test, the Kruskal-Wallis is more robust. This means that it's reliable in a wider range of situations. It's more robust to the violations of the residual assumptions. It's more robust, but on the other hand, it has less power than ANOVA. So this means that it's less likely to lead to a decision or to a rejection of H0. And this is exactly what we're going to see in our example. I will simply launch a Kruskal-Wallis test on exactly the same data and show you what I get in terms of p-values. So I go to test the hypothesis, non-parametric tests, and comparison of case samples. So I will fill out spiciness in the data field and the sauce and sample identifiers. Here you have options for multiple pairwise comparisons, which are adapted to Kruskal-Wallis tests. So I would recommend taking this option. In the charts tab, let me just activate comparison plots, box plots, and show p-values. I will show you what this looks like. So I click OK. If I go down, I reach the p-value here, which is higher than the risk threshold alpha, so we cannot reject the null hypothesis anymore. You remember with ANOVA, we had a p-value of 0.049, so we rejected the null hypothesis. We were able to make a decision. Here, we're unable to make a decision anymore. So non-parametric tests have less power than their parametric equivalents. Let me just show you the chart I have configured in the dialog box. There it is. So these are multiple box plots of spiciness according to sauce, and XLSTAT has automatically added the multiple comparison p-values above the box plots. So this is the p-value, for instance, linked to the comparison between S2 and S3. This is the one linked to the comparison between S1 and S2, and this is the one linked to the comparison between S1 and S3. Now I'm just showing it to you because it's very nice, but this chart in our specific case is not useful. Why? Because whenever your global p-value, this one, your global p-value is insignificant, it doesn't make sense to investigate multiple comparisons. You can investigate multiple comparisons only if your global p-value is significant. So let me move forward with the last part of this webinar. We've investigated the one-way ANOVA. Now we'll move to the two-way ANOVA and interaction effects. So here's the real data set. I've added one new column, the judge column. We actually have 8 judges or tasters or assessors. And each sauce is tested 3 times per assessor. Look, these 9 measurements are done by the same judge. There are 3 for each sauce. And then we have the same for judge 2 until judge 8. This means that there's some specific link that links these 9 first observations, a link which is due to the tasting experience of judge number 1. So maybe judge number 1 is more optimistic or overrates the spiciness in sauces according to the other judges. So there is a kind of a dependency among these 9 observations and dependency among the following 9 observations. This is why the independence assumption was not really true, was not really respected in the one-way ANOVA. Look at this sentence here. This independence assumption wasn't respected in the one-way ANOVA. But including the judge column in the model will solve the problem. Now, here are our new questions. Does spiciness mean change according to the sauce, according to judge, and according to the interaction between both? So for instance, if we get a judge effect, this means that there are judges who will overrate the spiciness or underrate the spiciness according to the other judges. And if we get an interaction effect, this is what I will be developing right after. This would mean that the effect of one factor depends on the category of the second factor. For instance, the sauce effect depends on the judge, or we can say it symmetrically also. So the judge effect depends on the sauce. And how can we represent this graphically? Let me show you very easy examples here. So this is a very simplified case with only 2 sauces and 2 judges. Among the possible outcomes, we can have these 4 outcomes. As you can see, within each chart, we have the judges on the x-axis and the sauces represented by different colors. So in black, you have sauce number 1, and in white, you have sauce number 2. In this first case, let us investigate the judge and sauce effects. Do we have a judge effect? If we average the 2 means for judge 1, so we get an average around here. And if we average the scores for judge 2, we get an average around here. And we see that the 2 averages are the same, so there's no judge effect. But if we average the black bars and we average the white bars, we obtain 2 different averages. This means there is a sauce effect. Then, next case, we see that if we average the scores for judge 1 versus the scores for judge 2, there's an increase in the average spiciness. This means that there is a judge effect. But if we average the black bars together and the white bars together, we find out that there is no difference between the sauces. So here we have a judge effect. Let us take this special case where things get a little bit more complicated. If we average the scores for judge number 1, we get an average around here, and the scores for judge number 2, we get an average over here. In this case, there's no judge effect. So we have the same averages. If you average the black bars together and the white bars together, we also get the same average. So there's no sauce effect. But actually, look at this chart. Something is happening. And what is happening? Actually, the sauce effect depends on the category of judge. According to judge number 1, sauce number 2 is spicier than number 1. And according to judge number 2, sauce number 2 is less spicy than sauce number 1. This is what we call an interaction effect. So the effect of one factor depends on the category of the second factor. In this case, we have some more complex outcomes. There is a judge effect. There's a global increase between judge 1 and judge 2. There is a sauce effect also. So if you average the blacks together and the whites together, you find out that there's a change. And also there is an interaction effect. Look at how judge 1 perceives the difference between the 2 sauces compared to judge 2. According to judge 1, there's no difference in spiciness, but to judge 2, there is a big difference. So here we have the 3 effects included. Now let us configure Twoway ANOVA in XLSTAT. Go to modeling data, ANOVA. So I capture spiciness in the dependent variables, and I capture my 2 columns in the independent variables, so judge and sauce. In the options tab, I will ask for interactions, and I will add here a 2, which means that I'm looking for maximum 2-way interactions. Anyway, I cannot go further than this in my case because I only have 2 factors. If I had 3, I could have investigated a 3-way interaction. Then in the outputs, something very important, which I recommend to activate automatically, is the type 1, 2, and 3 SS. You will see that effect tables can be expressed in 3 different ways. Unfortunately, I don't have the time to develop each way apart, but roughly I would always recommend relying on the type 3 SS. Okay. Of course, you can ask for normality tests and for tests of variance equality, and you can also ask for multiple comparisons within ANOVA. I clicked OK. First thing XLSTAT asks me for is which effects do I want to include in my model. I want to answer the judge question, the source question, and the interaction. Then which effects do I want to compute multiple comparisons for? Let me take all of them. Unfortunately, we won't have the time to comment on multiple comparisons outcomes. You can explore them on your own. Here, look, you have 3 tables of effects, type 1, type 2, and type 3. I will comment on this one. So each effect is linked to a specific row. We have judge, source, and interaction. And each effect is also linked to a p-value. I have included the null hypothesis for the 3 effects. So for the first effect, the null hypothesis says that the judges have equal means. Second effect, the sources have equal means. And the third effect, the source effect does not change according to judge. So we can reject all these hypotheses according to the p-values. But whenever you have a significant interaction, I would suggest relying on the interpretation solely of this interaction and maybe give some less importance to main effects, so judge and source effects. How can I interpret the interaction? So there's one specific chart which we call the interactions chart, which allows us to investigate this interaction. So the interactions plot represents spiciness on Y and represents one of the factors on the x-axis. So this is source in this case, and the other factor is represented with different lines, 1 line per category. Here we have 1 line per judge. I could have had the opposite, so judges on the x-axis and 1 line per source. What do we see here? Look at the purple judge and at the green judge. Okay, so this one and this one. According to those 2 judges, the source number 2 is less spicy than the 2 other sources. But if you look at the gray judge, this one, you notice that this judge finds that the second source is more spicier than the first one. So we don't really have the same pattern of tasting across judges, and this is how we interpret the interaction. So whenever you don't really have the same pattern across the categories of one variable, for each category of the second variable, this means that you have interaction effect. This is visible whenever you have lines crossing each other on this chart. So one possible conclusion here is that the panel of judges or of assessors is not trained well enough to evaluate spiciness. So this is an undesirable property we get in sensometrics. But you should know that in other fields of expertise, for instance, in agronomy or in design of experiments, sometimes a significant interaction could be very interesting. So it could mean that there is some synergetic thing happening between 2 factors. So this is another way of visualizing the interaction. This chart is provided by XLSTAT. You can find the option within the dialog box in the ANOVA. So to sum up, ANOVA is a modeling tool with a quantitative dependent variable and qualitative independent variables we call factors. ANOVA involves a test based on the between group and within group variation ratio. Assumptions about residuals are important to verify. Multiple pairwise comparisons help identifying which specific levels are significantly different. The Kruskal-Wallis test is a non-parametric equivalent to one-way ANOVA, and multi-way ANOVA helps investigating main and interaction effects. I hope I'll be able to talk to you once again next week on the webinar on supervised machine learning and prediction. So before saying goodbye, let me take a couple of questions. Can ANOVA handle the judge effect with more than 30 judges or panelists? Yes, of course it can, but actually there are other methods which may be more appropriate in this case, and these are mixed models that imply taking the judge effect as a random effect. How can I make data transform? How can I transform my data, for instance, to make the residuals a little bit more appropriate for statistical testing? Well, you can either use Excel, for instance. So you can use the log function of Excel and transform your data into logarithmic scale, so log spiciness, for instance. Or you can also use the XLSTAT variable transform feature, which is right here. So preparing data variable transformation. So you can select your data here, and there you have Box-Cox transformations, for instance, and other interesting transformations. Well, there's a question about this option in ANOVA. In the options tab, if I take model, how many, what does this number mean? This number means that what is the largest interaction you want to include in your model. So if you have 3 factors, for instance, you can include up to 3-way interactions, but you're not really obliged to include 3-way interactions. You can leave it to 2 here. Which is the differences between the 3 types of Dunnett tests available in the menu? There are 3 types of Dunnett tests. One type where you don't really expect in which direction the difference will be between the tested products and the control product, or the tested categories and the control category. And there are 2 other tests. In one of them, you have strong beliefs that the scores for the tested categories compared to the control categories will be higher than the control, definitely higher. And in the last case, you have strong reasons to believe that the scores for the categories compared to the control will be lower than the mean of the control. What to do when the ANOVA shows differences but the postdoc test does not, and how to run unbalanced ANOVA. This happens a lot of times. We've written an article on the XLSTAT Support Center that explains this very specific, this article, how to interpret contradictory results between ANOVA and postdoc tests. I will paste the link in the chatting window. That you can go and have a look to have an answer to your question. Can you explain the validation box available in ANOVA? If you want to know more about the validation tab, please subscribe to the machine learning webinar we'll be seeing next week. I hope I'll be able to talk to you once again next week. Have a very nice day, and bye-bye.